All right, everyone. So welcome to this week's edition of GROOT. Today we'll be hearing from Miika Tuominen on completions of theta n spaces.
Yeah, thanks. All right, so most of the talk will be just discussing like a completeness, and I guess the completeness can refer to many different things. So this is completeness as in complete Segal spaces, which you might have heard of. So let me start with something that is hopefully something fairly familiar to at least most of you, and that's with classifying spaces. So classifying space. All right, classifying space, it takes in a group, or more generally a groupoid, and then it outputs a space, or what might be thought of as an infinity groupoid. So it's kind of making the groupoids homotopy coherence. And for me, infinity groupoids, I'm going to define them as complex. Right. And this is kind of a special case of the nerve functor that takes category and then outputs a simplicial set. Okay. So this is kind of the idea of taking something kind of fairly strict groupoid here, and then making it homotopy coherent. And then, okay, we can do this kind of same procedure for like other kind of objects. So we could take categories, okay, groups, in particular CCN categories, and then we might want to somehow embed that into infinity categories by some kind of a functor, so that this kind of square somehow commutes properly. Now, for me, infinity categories, I'm gonna define them as complete Segal spaces that we'll be discussing a little bit later. And now, okay, so the question might be, okay, what kind of a nerve functor would I put here from categories to infinite categories? Now, when working with this model of complete Segal spaces, there's a kind of a naïve choice of a nerve functor here. That's just kind of extending, taking this nerve functor and now kind of discretely including these kind of or simplicial sets into simplicial spaces, and that gives something. But so here the I guess the naïve choice fails this completeness part of these complete Segal spaces. So that's where this completion functor kind of comes into place. It allows us to sort of correct this failure of completeness for this naïve choice or any other construction that you might want to consider in this particular model. So maybe there's some kind of nerve here. And then you can go even further. We might go to higher categories here, and then the homotopy coherent version would be then infinity n categories. And then you might want to sort of you might hope for some kind of nerve functor here as well. Now, again, here there are some naïve choices, I guess, but here there's kind of no fully homotopy coherent version known for, regardless of whatever model we take for infinity n categories. But for me, infinity n categories are going to be complete the Segal theta n spaces. And here we can also discuss these completeness conditions and what it means. Okay. Okay, any questions here at the of this setup at this point? And I should mention, feel free to interrupt me at any point. I also have a chat open. Might fail to pay attention to it, but so do let me know if I miss a question there. Okay, so then let's kind of recall what these, for example, complete Segal spaces are. So first, just So delta is gonna be the simplex category. So this has objects. They are given by natural numbers, positive, non-negative integers. And this is going to be the poset of these integers from 0 to n. And non-negative integer. And then morphisms. Since in this category, we order preserving. Functions between these posets. And then we define the category of simplicial sets as the category of functors, contravariant functors, from delta up to the category of sets. And I'm going to be considering this kind of with a kind of homotopy theory that is so these can be thought of as kind of spaces. So this up to homotopy kind of equivalent to topological spaces. And then further, so then category of simplicial spaces, I'm going to define as contravariant functors from delta up to kind of spaces, which is now for me these simplicial sets. So this means okay, simplicial and then spaces. And another perspective you can view them as is as bisimplicial sets instead. So this is the same thing as contravariant functors from delta cross delta to just sets. Both of these perspectives are very useful. But here kind of the two copies of delta behave very differently here. So that's why kind of a simplicial space, kind of one of them is kind of playing similar role as the simplicial direction here, and then the other. So this is kind of a version of the simplicial sets, but kind of enriched in spaces in some sense. Okay. So that's the entire category, but similar to how Khan complexes is just a subcategory of these simplicial sets that really model the spaces. So then kind of the really kind of infinity categories within this category of simplicial spaces is just some particular objects that define as follows. Okay, so first, so if we take X, that is a simplicial space, we say that it is a Segal space if it is first a fairly kind of technical assumption about it being injective or equivalently really vibrant. So maybe the term simplicial space might be more appropriate to just any functor that is injective vibrant, because in particular, this condition guarantees that whenever I take any simplicial degree here, then the output is going to be a Khan complex, so a space. And then it also gives us various kind of vibrancy conditions that allow us to, or making things more homotopy coherent in the theory. It's kind of I guess you can also think about this as analog of considering CW complexes within spaces. It's kind of a very nice subcategory of objects. And then okay, that's the first condition. And then second is that then we require that this object is local with respect to these so-called Segals. Which are the following. Okay, so if we take a kind of sequence of kind of morphisms in a sense, one cells in our simplicial space. And then we kind of take wedge of them, so take a push out along a point of multiple copies of this object. And now this includes into, if we take the representable at the n simplex, that then, okay, this is kind of a spine inclusion map. So, okay, let me make it right. So here the F is kind of a discrete unit embedding. So if we have a delta unit embedding takes these two functors from delta up to Z, and then further the sets can be discretely included into simplicial sets. And this composite here is the functor F. So that's a kind of discrete unit. So what this is kind of saying, for example, when n is equal to 2, we get that, okay, here on the left, we have this kind of diagram. So 2 copies of kind of a one simplex glued along this one point. And that's including into a 2 simplex. And so what this Segal condition allows us to do is kind of define a composition. So if we have a kind of 2 composable kind of morphisms, then there is some kind of another morphism that is a composite of them too, and then this composition is somehow witnessed by kind of a 2 cell. So this allows us to define a composition within a Segal, within a simplicial space. And so this allows us to kind of somehow consider these Segal spaces as something category-like objects. And it turns out that Segal spaces, at least up to homotopy theory, is put into categories internal to spaces. Now, the prototype model for infinity categories would be categories enriched in spaces. So this is something slightly more general. So that's where the completeness kind of a condition will fix this kind of a discrepancy. So this internal means that not only are they mapping kind of the hum, spaces have additional structure of being a space, but also the objects are kind of a form of spaces as well. Yeah, when the internal setting. Okay. And then a Segal space is complete if further its local with respect to this kind of map where we're taking this one particular object E and then mapping it to a point. So the point is same thing as the representable at the 0 simplex. Now, before I tell you what this E is, let me maybe discuss what the kind of implications of this being local with respect to this map is. So this E object kind of encodes. So this Segal condition allows us to view these simplicial spaces as something category-like objects. So this E somehow encodes the equivalences within that category-like object. So encode. So in this our Segal space X, it will be viewed as a category-like object. And so if we look at kind of the space of maps from this object E to our X, so this would be somehow the space of equivalences in X. Right, and being local with respect to this map here means that if we look at this map that's induced on these mapping objects. So here, this is just isomorphic to the 0 level of X. So this is saying that this is a weak equivalence of spaces. And now, just being injective vibrant, this is also, I guess, homotopy equivalent to the maps from this kind of one simplex to X, where this is kind of encoding paths or like homotopies in X viewed as a kind of simple object. So what this completeness condition is doing is, so we have two notions of equivalence. We have this equivalences viewed as a somehow category-like object, and then homotopy equivalences when we view it as a kind of a simple object. And this completeness condition makes these two notions coincide. And then complete Segal spaces. Or we also call it CSS for short, abbreviated. This is at least up to homotopy theory is equivalent to categories enriched in spaces. Which is the definition usually of infinite categories. Any questions at this point? Okay. So then, okay, what is this E? So let's consider some various adjunctions or kind of various nerve constructions. So, a very kind of common way to create adjunctions is the following. So if we want to say, for example, create another adjunction between simple sets and say categories, a way to do that is by taking a functor from delta to cat. For example, canonical choice would be kind of the inclusion, because objects of delta can be viewed as categories. They're posets, so in particular categories. And then here we have the Yoneda embedding. And whenever we have this kind of functor, then there is a kind of a extension of this functor along this Yoneda embedding that gives a functor here. And it always has a right adjoint like this. And then the usual nerve is, in fact, this right adjoint here. And now this we can include to our category of simple spaces discretely. And here we have the composite of F. And now our discrete nerve that I'm going to denote n sub d is a composite of this nerve with the discrete inclusion here. And now, based on this kind of construction, it's relatively simple to show these functors are all fully faithful. Yeah. So this both nerve and the discrete nerve. Now that's one way to consider it. There's a kind of other similar kind of a way to consider it. If we consider instead the kind of Yoneda embedding of the delta cross delta to simple spaces. So this is just a regular Yoneda rather than the discrete Yoneda. And then, okay, we can map delta cross delta to categories where now this functor is essentially the same as So in this first copy of delta, we're just including them, and we're just taking constant in the second copy of delta. And then based on that, we again an adjunction where the discrete nerve would be the right adjoint in this thing. So usually when we consider these nerve constructions, I mean, this is usually kind of the setup, we take some kind of a diagram of our shape into our category where we want the adjunction between, and then it's induced by this kind of general construction. And then that gives us always, in particular, it's a right adjoint, and then oftentimes you can check that, okay, it also respects somehow homotopy theories and maybe has additional properties like being fully faithful and stuff like that. Maybe another example, maybe a more familiar example of this kind of construction would be if we consider delta going to topological spaces, taking n simplex and then making out of that the geometric n simplex. And then, okay, here we have the unida embedding. And now here, the adjunction is introduced by this geometric simplex functor would be the usual kind of equivalence between topological spaces and simplicial sets. So here we will have a singular chain, singular simplicial set functor, and here we would have the geometric relation. So many constructions between these kind of pre-sheaf categories fit into this framework. And okay, we have a maybe for this discrete nerve, we also have an explicit formula, at least level-wise. So if we take category C and apply this discrete nerve to it, okay, so now if I view this as a bisimplicial set, I can evaluate at both of the simplicial degrees, P and Q. Then this would be just the functors, set of functors from this category of brackets P to C, and it's a constant in Q, so it doesn't depend on Q in any way. And now, since it doesn't depend on Q, you might expect, okay, it's not necessarily very well behaved, and that's precisely has to do with the why it fails the completeness condition. We are not really utilizing both of the simplicial degrees here. Okay, so if we denote I of, say, Q to be the connected groupoid with Q plus 1 objects. So for example, if we take I of 1, this would be just 2 points and a single isomorphism between them. So in general, in this I of Q, we have a chain of Q isomorphisms. So now the E that I had before, that would be the discrete nerve of I of 1. In general, I denote E of Q, I define that as a discrete nerve of I of Q. Right, so since this walking isomorphism I1 here kind of encodes somehow equivalence of categories, then this discrete nerve somehow takes them to something similar in this homotopy coherence setting. Equivalences in the simplicial space world. Okay. So as I mentioned, this if we take the discrete nerve of a category, this is now this is always a Segal space. So whenever we have a discrete object, it's already injective hyperant. And then because categories, we have this composition, then that composition in fact makes the kind of a Segal condition to be true like in a very strict manner. But usually this is not complete. I guess not complete. In fact, precisely characterize when it's complete or not. If it's not complete if C has a non-identity isomorphism. So that means somehow this discrete nerve is to capture kind of the isomorphisms or equivalences in this category C. And that's what we want to fix if we want to make this kind of nerve construction that also has this completeness property. Right. So then kind of fix comes from Rezk, who also the complete Segal space model structure is also by him. And he gave this nerve, kind of fix to this nerve. That's level-wise can be given as follows. So here, okay, we still take kind of functors. Now we have the P simplex. But now we want to use this simplicial degree Q somehow to encode the isomorphisms in this category. So we can take I of Q here. So chains of Q isomorphisms, and then we go to C. So this is the last definition. Now, if you've seen this classic, other name for this Rezk nerve is classifying diagram, and if you've read his original paper on complete physical basis, it's expressed slightly differently. There, it's described as a nerve of this taking isomorphisms in this mapping category of from P simplex to, and then evaluating this at degree Q. You might be more familiar with that description. Okay. But now, okay, we can modify this, adjust this kind of this description a little bit to a different form. Now, because the discrete nerve is a fully faithful functor, we can apply to both of these sides in this Hom set, and we will get an isomorphism. So then this would be now Hom in the category of simplicial spaces. And when we apply the discrete nerve to this P simplex, okay, the nerve is an extension of the unit embedding, so we just get the discrete representable at P. Now this E of Q I defined as the discrete nerve of the I of Q, and the discrete nerve is also right adjoint, so it preserves product. So I can express the left-hand side like this, and then here we have the discrete nerve of C. Right, so all of these nerve constructions where, okay, of this form, where we have some kind of diagram here, and then mapping to our object C. So now looking at this, this is saying that, okay, this Rezk nerve is in fact some kind of a nerve construction defined by this particular diagram, by simplicial diagram like this, applied to this discrete nerve. So somehow you can think about so this Rezk is the completion, the discrete nerve. Right, so I guess, yeah, I should mention that this N of C is always a complete Segal space. So in fact, kind of encoding these isomorphisms at all levels, like independent of this degree P, allows us to capture these isomorphisms as well, and then that will impose the completeness condition for this nerve. Any questions at this point? And this Rezk nerve has many other properties as well. It's fully faithful, like the discrete nerve. Then also, if you consider like the appropriate model structures in these categories, then it's also right equivalent and it also preserves and reflects isomorphisms, equivalence, and so on. As much as that could be said about that. So okay, so since this is a kind of completion of the discrete now, then we can use that to kind of inspire, okay, what would be the completion of any old Segal space. So let's so if X be a Segal space, but maybe missing the continuous condition, then we define this kind of X tilde, which is also a simplicial space. And we define it kind of level-wise, so we evaluate at both the simplicial degrees. We can take something similar to what we had here. So we have the kind of representable part of a discrete representable here. We take this object that encodes these equivalences. But now, since we are no longer dealing with a discrete, then we also should include the representable for the kind of space part, which is going to be this kind of constant simplicial object. And I'm going to use this degree Q also to encode that. So if we were to just take these two, that would be just the representable functor at the P and Q. But then we are including this also taking product of this E of Q to encode the equivalences in our object X. So we define like this. So this is how we in the category of simplicial spaces. Now, something to note here that we have the degree Q now appearing here in both of these places. No problem. This is kind of a diagonal operation that we are doing here of putting that kind of so we could consider these as separate kind of co-simplicial objects, and then taking kind of a diagonal to get this. And this kind of diagonal procedure can break the injective vibrancy assumption on our Segal space. So then completion, so then define X hat. Okay, so the completion of X denoted by X hat is an is the injective vibrant replacement of this X tilde. So there's kind of form, whenever we have a kind of model category setting, this is kind of a kind of canonical functor that takes an object and then replaces it by a vibrant object. Now, you could use kind of that kind of general kind of model categorical construction to also get some kind of that completes Segal space, but then it doesn't have necessarily all very nice properties. So this particular kind of a completion has additional properties. So this is a theorem by Rezk again in I think O2 or somewhere around. That this particular completion is very nice. So okay, we first have that this X hat is indeed a complete Segal space. Now this completion also comes with that kind of functor. So there's a kind of canonical functor that somehow includes this X into X tilde that I'm gonna, and this is kind of real. And then further, okay, so this map IX is a, okay, this is something called a kind of trivial of vibration. So that means that it's an inclusion, and then it's somehow this map is local with respect to all the maps that I mentioned before. So it's a level-wise weak equivalence of spaces, and then it's also local with respect to the Segal maps, and also the completeness map as well. And these two together is saying that this is a vibrant replacement. But then we also have an additional condition that this I of x is also something called a decay equivalence. So if we have just a level-wise equivalence of Segal spaces, then that's always a Segal, decay equivalence. But then when we have kind of weak equivalences in this more kind of localized setting, then that's not necessarily true anymore. So this is saying that this is a very particular, kind of nice vibrant replacement for this. So this decay equivalence means that that this I of x induces an equivalence of homotopy categories. And furthermore, that also induces equivalences of this kind of mapping spaces. So that means that this vibrant replacement is also kind of compatible with this enriched structure that these Segal spaces have. That is up to homotopy. Okay. Right, so that's a kind of a classical kind of a completion. Any questions about this before I go to the higher category world? Okay, maybe I should mention also that having such a kind of a nice vibrant replacement via a Dweck-Hahn equivalence also means that there's some kind of correspondence between kind of as a corollary, you get that there's a correspondence between these equivalences in this kind of local structure and these decoequivalences. So that means that any weak equivalence is also like a decoequivalence between, say, Segal objects. So that's a very nice property to have, because usually kind of the weak equivalences in this structure, in the local structure, can be very pathological. So then getting this decoequivalence kind of makes them more tame in a sense. Okay. So let me maybe briefly kind of recap some things about high categories. So we define any category to be a category that is enriched in n-1 category. So it's an inductive definition where you can consider, say, 0 cat is a set and 1 cat is the same as category. Right, so that means that in any category, whenever you have two objects, then there's an n-1 category of kind of functors between those two objects. Right, so you can also describe it. So we have it consists of data of objects. So these are some points, or you can call them 0 cells. There's somehow morphisms, or maybe one form morphisms more precisely, or one else. So there are kind of arrows between these objects. So then we have somehow two morphisms, two cells there's different terminologies that you can use. So if we are given two one cells between the same objects, then we can consider two cells, like morphisms between morphisms. Right? So if we look at these two fixed objects, then the kind of morphisms between them form a category, where the objects are these arrows, and then the morphisms between in that category would be these two cells. And then we keep going on up to n cells between n-1 cells that kind of share the boundary. Okay. And a particular kind of a functor that I want to consider here between categories of various dimensions is a kind of a suspension. So this suspension, so this is kind of bipointed suspension. And what this does is it's a n-1 category, and then outputs a n category. So what it does is somehow takes this n-1 category and makes it a kind of this hom category for a particular between two objects in a n category. So we have that this if we take say n-1 category C as objects of just 2 points, 0 and 1, and then kind of the hom category from 0 to 1 here is precisely now n-1 category C. And then the other categories are something that's very interesting. So if we take say the other direction, we have no morphisms in the other direction, and then between the objects and themselves, we have just identities. So kind of the picture is okay, we have these two objects 0 and 1 here, and then somehow between these we have a kind of C's worth of kind of a morphisms going between them in this direction. Right. So this is kind of strict ed categories. So then what is the homotopy coherent version? So for us, the rule for kind of infinity categories was based on, we were considering this nice subcategory of categories of delta that somehow generated all the data. So I mean, in particular, categories is just joined by the just a walking morphism, but then this delta also encodes some of the composition structure because we have the higher degrees increases. And we want to get a kind of higher dimensional analog for like n categories of this delta. So okay, and then that is going to be the category theta n is a solution there. So we can define, okay, theta 1 is delta, or you can even go lower than that. You can take that theta of 0 to be just a terminal category. And then it's an inductive definition, where then theta n is the full subcategory of n categories on a particular set of objects. Okay, so we have first we have a non-negative integer m, and then we have a sequence of objects from theta n-1. M copies of them. So, and so this is kind of defined by taking kind of, so in particular theta n-1 So these are going to be in theta n-1. So they are n-1 categories in particular, so we can take their suspensions. And then we are somehow taking their wedge, so joining them at the kind of at the terminal objects. At one of the objects there. So we're taking chain of all of these. So the picture is somehow, for example, if n is equal to 2, we can take an example. For example, we take a 3, and then we need some elements of delta. So say, for example, 1, 0, and say 2. So this would be at a 2, and the picture would be the following. So we have since we have 3 here, so that means we have 4 points. And then, okay, we have 1 here. So we are suspending the delta 1 here. So that means we have a 1 morphism between here. So this one simplex has 2 objects, which are represented by these morphisms here, and then 1 arrow between them. The 0 simplex just has 1 object, and then the 2 simplex has 3 objects and these 2 morphisms, as well as a composite. So this picture would kind of represents this particular element of theta 2. And then you can kind of imagine for higher end, so you might have different arrows here, and then like a high dimensional arrows between them, and so on. So this is somehow the kind of a proper analog of delta for these higher categories. So if we were to just take these kind of suspensions of the one simplex, that would kind of give us the intel, which is kind of the generating object for any categories. But then taking these kind of these wedges, chaining them together, also allows us to encode the kind of composition structure within this subcategory. So then so we can consider contravariant functors from this category theta n to simplicial sets, but these are now theta n spaces. Okay, so this is gives our category, and then okay, a little bit short on time, so let me go fairly quickly on this. So okay, so for here we again take some kind of a particular subcategory of the kind of the infinity n categories. So so if we have a say x in here, we say that x is Segal if first it's again injective or really vibrant, they coincide in this setting as well. Again, that's fairly technical condition. But then 2, we have kind of Segal condition. This kind of Segal map. So if we take this kind of object where we have just one length 1 and some kind of chains, and then something suspended. So this is essentially just a suspension of the theta 1, and then take the discrete representable, and then wedging a bunch of these together. And these includes to theta. So if we take m and then the sequence of these. So this gives us kind of a Segal condition, but now this gives the kind of Segal condition only in the composition of the kind of one cells. But then we also need kind of Segal condition for the enriched structure. So then also to say that also enriched in Segal theta n-1 spaces. So it's kind of inductive definition again. And then complete X is further complete if we also have a locality with respect to somehow analog of this map from E to P, but we can include, so this E was somehow one categorical object, we can somehow include it into these high categories by just taking nothing interesting in the high dimensional, no high dimensional data at all. and that gives us a property motion. So we can ask locality with respect to this particular map. So here, by side is going to be the inclusion of into these theta in spaces, and then also enriched. So we also have a enriched completeness in the enriched structure. Complete theta n-1 spaces. So okay, because of this kind of inductive conditions, so we have a total n Segal conditions here. So we have these one new conditions, and then here we have a n-1 Segal conditions. Similarly here, okay, we have one new completeness condition, and here we have a n-1 completeness condition. So we can ask about kind of completion in each of these kind of degrees separately, or we can complete them separately in each degree. And in my kind of thesis work, I have created kind of constructions, generalized this completeness construction, so that I can complete in any of these degrees kind of independently, but also kind of together. So then just write a theorem that so there is again now a construction that takes a theta Segal theta in space somehow to another thing, so that on this x hat is complete in all degrees. So this is just a Segal in all degrees. Now this ix is again somehow acyclic cofibration, whatever that means. So that means that it's a vibrant replacement. And then further, then we have also something that's similar to the decoherence here. So that IFX is equivalence on homotopy categories, and then also on the enriched structure. So induces also these kind of vibrant replacements. On all kind of iterated objects. So maybe let me end there.
Okay. Thank Miika for a wonderful talk. Great. And does anyone have any questions for the speaker? All right, so if not, then let me go ahead and stop the recording, and let's thank Miika again.